To better understand the moon's role in mapping space, we first have to think about gravitational waves. Gravitational waves were theorized far before they were actually confirmed. And as with so many other concepts of the universe, it was Albert Einstein who first proposed them, back when he was crafting his most famous theories on space-time. He thought that sufficiently energetic events in space would cause gravitational waves, which are ripples in space-time, similar to ripples in a lake. Einstein's first predictions were made in the early 1900s, but it wasn't until the year 2015 that researchers were able to directly measure gravitational waves for the first time as they passed by Earth. A feat achieved by the Laser Interferometer Gravitational Wave Observatory, or LIGO, which is the main focal point for an ongoing international project. While gravitational waves are created by massive and destructive cosmic events, as Einstein said, events like black holes colliding and supernova explosions, by the time they reach us, they're more like tiny vibrations. But still, they've become absolutely vital in plotting what's what and where's where in the universe. The successful measurement of gravitational waves is already widely held as one of the most significant breakthroughs in recent times, giving researchers, as it has, an entirely new way to observe space. Before they had gravitational waves, astronomers relied almost solely on radiation, such as visible light and microwaves, to measure and observe objects. But gravitational waves are independent from all that. So much so, it's been said that the introduction of gravitational waves was like science and cosmology being gifted an entirely new sense. Before, we had only sight to view the universe, but now we have sound to hear it. It's not like these are especially loud sounds, though. When gravitational waves pass through Earth, they're totally indecipherable for most of us. They're tiny subatomic murmurings. But this means that, in some cases, researchers can use the waves to essentially see objects that are normally invisible. Black holes, for example, are traditionally only noticeable by the effect they have on objects around them. But now, they can be detected via gravitational waves too, by tracing the waves back to their source. This is extremely intricate science, however, which is why it's good news that a new way has recently been developed to measure gravitational waves with greater accuracy. And it's a method that makes use of our very own moon. Although theories have been around since the late 1970s, it was in 2013 that a team at Columbia University showed that gravitational waves might affect the orbits of binary systems specifically. A binary system is any system in space where two objects orbit a common center of gravity. Binary star systems, for example, have two stars rotating around each other instead of one solitary star, like our sun in the solar system. But binary systems don't need to be based on stars alone. Any two objects can pair together in this way, which is why the Earth and Moon can be said to be in a binary orbit as well. What's important for today's video, though, is that there are slight differences to be found in the orbits of binary objects before and after a gravitational wave passes through them. It's as though the wave leaves a trail of cosmic evidence in their wake, which can then be converted into information. Wave experts can extract data about the strength of the waves, for example, and can therefore predict what might have caused them, and where and how far away from us that cause may have originated. Regarding the Moon and Earth, then, the Moon's orbit is very slightly affected by the gravitational waves that reach us. And so, seeing as researchers can measure the lunar orbit to within a centimeter, we have a surefire, near-perfect way of tracking gravitational waves right on our doorstep, and therefore a close-to-home base from which to paint a picture of the rest of the universe. This new application of the science comes following research by physicists Diego Blas and Alexander Jenkins published in the journal Physical Review Letters in March 2022. And at this early stage, it's thought that by essentially converting the moon into a beacon for gravitational waves, we could soon be measuring those waves with significantly more accuracy. In some ways, it's like we're finally seeing or hearing the universe in high definition. Thanks to this new technique, it's hoped that we should soon be detecting more gravitational waves than ever before, and seeing them clearer than ever before as well. Which is exciting for a number of reasons, and especially for anyone interested in producing a map of the universe. What's particularly important about gravitational waves is that they provide us with unchanging, reliable markers in space that aren't affected very much by the surrounding cosmos. While more traditional astronomy relies on radiation, we know that much of it can be distorted. Light can pass through dust clouds, for example, and dim as a result, or it can be altered and bent by gravity, so that what we see through our telescopes isn't a true representation of what's really there. But gravitational waves, by comparison, travel through the universe relatively unhindered and reach us in near pristine condition. But still, why are they so useful in the first place? Again, it has to do with their uniformity. If you know how to read a gravitational wave, then you know how to read a constant of space. It can reveal to you details about anything from the expansion of the universe to the most violent and formative physical events that happen within it. And it can even provide a glimpse into the very first moments and birth of the universe too. But really, those are only the possibilities that researchers can currently imagine. By viewing waves through the lens of lunar orbit, we're truly looking at space in a whole new way, which could also lead to whole new discoveries. Naturally, one of the best parts about this research is that it doesn't require us to build anything new to put it to use. The moon's orbit has always been there. We don't need to affect it in any way, we just need to keep a close eye on it. And automatically, we'll gain a better understanding of gravitational waves and the universe as a result. And although the calculations involved are difficult, we have everything we need already in place. When NASA first put humans on the moon during the Apollo program, one part of the mission that's often forgotten is that astronauts left mirrors on the lunar surface. Today, researchers on Earth can simply fire lasers at those mirrors and wait for the light to reflect back, to determine exactly how far away the moon is at any given moment. We already have a firm grip on how the lunar orbit works then. It's just that by pairing it with gravitational wave activity, we're applying that knowledge in an all-new way. Of course, we know that it's not as though the Earth-Moon setup is the only binary system around. Astronomers do and will apply similar methods to other binaries too. Anything that helps clear the fog with gravitational waves is certainly worth pursuing, but it still feels particularly notable, hopeful, and exciting that our greatest wave detector could well be bound to our own sky. The unerring presence of the moon is already a source of comfort for many, but now it truly is a bridge between us and the rest of the cosmos. We're using it